Hey guys, so I just wanted to share my 90% kinda complete project. Um, so basically, the big idea is my prediction is companies with larger market caps are easier for machine learning models to predict than companies with smaller market caps. And that's like the big idea. So keep that in mind throughout like everything I say. I'm just gonna give a hopefully quick walkthrough through it. If you want all of the code, I'll have like a GitHub link. You can find that link, and if you're confused at how, just like I don't know, send me a message. Once you clone the repository, you'll have to do the whole virtual environment thing, which can be found on the README. If you know how this works, then just follow the instructions, copy paste the code in, right? And then install the requirements. If you don't know how it works, a quick YouTube video on how to install a virtual environment and how to install necessary dependencies should get you there. Okay, so I did a few attempts already. Here are the past attempts, right? I was trying to like use machine learning models to predict stock prices in the future. And it kind of landed with this, the seventh one, which, as I said, it's me testing my own theory, my like assumption that market cap makes it easier for machine learning models to predict price. This is based off of the intuition behind fama-french, which I don't really know how to explain rigorously, but the intuition behind it is that in a portfolio, let's say the portfolio returns 10%, right? There's a systematic portion of it, like let's say 0.5% of that 10% that is completely responsible for like one factor. That factor being size, right? Generally speaking, and it's been proven, I don't know where the papers are, but it's been proven that companies with smaller market caps tend to outperform companies with bigger market caps. Intuitively, that kind of makes sense because companies that are already big, they don't really have room to grow. Companies that are small, they could skyrocket due to many different reasons. Obviously, small companies can also go bankrupt a lot more commonly than big market caps companies. But people tested it. The people who wrote the papers on fama and French, they tested it and they found that there are a few factors that are just built into portfolios that essentially say asset managers aren't as good as they think. They're not actually like making alpha as they say. It's kind of just like, oh, they're leveraging themselves in these systematic risks. Yeah, but that was kind of a ramble. Let me just continue on explaining like what I actually did. So first things first, I imported everything. Quite frankly, I don't think I use all of them. I just carry them over from the past attempts. I copy paste all of the libraries because in certain attempts, I tried different things, right? I believe in the fifth attempt, I tried to do something with standard deviation, try to like emulate volatility and try to use a machine learning model to predict that. It didn't go as well. But yeah, I just copy pasted this. I use most of these and yeah. I'm going to go through all of the functions that I created, which ends up printing like the quote unquote proof that large market caps are more easily trained. And I'll explain that a bit later when I get there. So this function, it's data prep. It essentially takes a ticker and then returns a big data set of the ticker's entire stock price history. And the way it's broken down is the X, if you guys know machine learning stuff, the X data set is the past 100 days, or it's whatever days that you choose, but I chose 100 days. And then the Y is tomorrow's price. The split percentage here just dictates what percentage is in the train and what is in the test. So by default, it is 90% into the train. Okay, so this section just accesses Y-Finance, takes the ticker, and prints the entire stock price history. This is for the stocks that sometimes don't have dividends and stock splits. I found that when I tested this and I tried to loop it into all of the S&P 500 tickers, that it sometimes ran into errors. And I found that it was because some stocks just don't have the dividends and stock split column in Yahoo Finance. Okay, so this thing just, it's what gets us the past 100 days. It shifts the columns and it makes the data frame have 100 days of past data and 1 day of future data, which is tomorrow's price. Now this is where we like start prepping it for like the actual machine learning stuff, right? As a general principle, it's probably better to scale all your data to be within the range of 0 and 1. That's just what the machine learning models, the neural networks say. It takes in the data better that way. So you scale it, so you turn everything that you did up here into a number between 0 and 1 that still like matches. It's like still, it's, what's the word? Proportional, I think. And then you turn like, this is essentially just the first 101 days, right? Because you went 100 days back and then you have today's price. So that's 101 days. And then this is tomorrow's price. And that's the X. X is the past 101 days. Y is tomorrow's price. And then split is just converting this percentage into the actual number that you're splitting the entire data set by. And that's how you do it. I have to reshape it because for some reason, the LSTM model, the machine learning model, doesn't take it in that well if it's not reshaped like this. So yeah, there's not really much explanation. I've done this through all these past attempts. It's just what works best. Okay, so that's the first function. Let me just close that. The second one is compiling data. It's just a repeat of data prep, but for a list of tickers. So let's say I have a list of all the S&P 500 stock tickers, right? I put it into data prep. It doesn't work because data prep only takes one ticker. Compile data is a function that takes multiple. Same days ago, same split, but it first preps up a X train, X test, Y train, Y test, all for the machine learning thing, reshapes it in order to fit and like actually append better when we do the for loop. Then it loops through all of the tickers in this list, which by default is just 2 tickers because I wanted to test if it even worked, and it does. So it loops through all of it. It first calls on the data prep function, so it makes its own X train, X test, Y train, Y test of that particular stock, right? And then it appends the new ones onto this empty data frame. And then it keeps appending and it keeps appending. So it goes Apple first. It takes Apple's entire historical data, turns it into the 100 days ago and tomorrow, splits it up to train and test, and then puts it into this empty NumPy array. It's a NumPy array. And then it goes on to NVIDIA. And then it goes on to like Google or something. And then it goes on to Amazon. And it makes this gigantic X train of whatever list that you have. So that's what compiled data does. Okay, let me close this. This is the next thing. It reads an index. Essentially, I just took a file, a CSV file from the internet. I just searched up S&P 500 list, and it just takes it, whatever you have in your folder, and then it turns it from a CSV into a data frame, and then that data frame into a list. It then loops through a few blacklist stuff, which by default I put as this. I just found that these didn't work well with Yahoo Finance. The B class stocks in particular, I don't think they have stock data like at all. They don't have price data. And then these are stocks that I believe are so recent that they don't have 100 days worth of stock price data, I believe. They just didn't work when I tried to loop them, so I put them on the blacklist. So just to reiterate, this takes any file of CSV that has stock tickers, right? Let me just show you the CSV. So it literally only concerns this first column of symbols, right? They're stock tickers. It loops through all of them, turns it into a list, and returns the list of tickers. So that's read index. Next one is get index market cap, which should be get index metric as a whole. Essentially what this does is it takes that list of tickers and then it takes a metric, which I made a list of metrics here. It's like a whole bunch of things. And it finds on Yahoo Finance the most recent of it. So for example, let's say I put the list of S&P 500, which I use from here. Using read index, I find my S&P 500 tickers, I turn it into a list. I'll put the list into this function. And then let's say I choose a market cap, right? For metric, it essentially goes, okay, Apple, find Apple. Okay, we got Apple, we print Apple's ticker. And then after that, we look for on Y Finance's ticker function, we look and we find market cap, the current market cap, by the way. I did not touch anything historical. I'll talk about that later why I didn't. It was just very difficult. So it takes that number and appends it onto a NumPy array. We turn that NumPy array into a data frame, and then we turn that data frame into a grouped object by their quantile, which essentially just means, so we have 500 market caps, right? Because there's 500 tickers in the S&P 500. We have 500 of them. What is the lowest 10%? So the lowest 50 market caps, the lowest 20% market cap, all the way to the highest 50 companies market cap, if that makes sense. It's split into quantiles of 10%. I think that's the right way of saying it. So overall, get index metric, this function takes in the list of tickers that we want and then a single metric that we want to explore, and it turns it into, the output is a grouped object by what is it? It's the grouped object of whatever metric you want to measure split into the actual values ranked. Okay, I hope that makes sense. So that's get index metric. After we get that, we have to turn that grouped object into something else, right? So essentially what grouped into trainable data is, well, it turns the grouped object into trainable data. It's not only trainable data, it's also testable data, which I'll talk about later, but that's just a name right now. First, define a dictionary, and this is for the sake of tens, because here I split the data into 10, right? There's the lowest 10% data, there's the in-between 10% and 20% market cap, there's 20%, 30%, market cap 30%, 40%, is split into 10. And in grouped into trainable data, it's just by 10. Now we're going to loop through the grouped object. We're going to save variables, right, in the dictionary with the name of whatever percent it was and the box. Then we're going to run compile data on the actual list. This is the tickers that belong in the group. So let's say you're looking at the group highest 10% market cap. You'd automatically assume, like, through your intuition, and you'd be correct that like Nvidia and Google are on the list because they have big market caps, right? So Nvidia and Google would be on the list here. And as we discussed before, compiled data just takes a list and then takes every single one of the tickers in the list, turns it into an X-train, X-test, Y-train, Y-test, and then combines it all into one big X-train, X-test, and all that. Then it returns the big dictionary of all of the data. Okay. Next one is actually training the model. What are we doing? Essentially, what the function takes in is the dictionary of data that we got from the previous function and the metric, just to be like sure. Because the metric, it's literally only called upon here to be a name. Like basically what you're typing in here is just going to be a name of a folder. That's it. So first, you do all the model stuff. For those who are unacquainted with LSTM stuff models, this is TensorFlow, which is a library that is used for like machine learning stuff. Quite frankly, you don't really have to understand this. I'm going to walk through it really briefly. The model is sequential, so it takes data in a, sequential order. The input is 101 because it takes in the data of today's price and then 100 days worth of prices in the past, right? Or at least I slowly condense it down from 100 to 66 to 33 into 1. 1 would be the output, essentially tomorrow's price. So we funnel it down from 101 all the way to 1. These are dense layers, which means they have activation functions. You don't have to understand what that means. Essentially, it's a way of adding complexity to your model. Because what a machine learning model is just an algorithm that repeat guesses something based off of data. It just guesses and then adjusts, and then guesses again and then adjusts again. The more adjustments or ways to adjust that you add into the function, the more quote unquote complex it gets, and the more quote unquote accurate it should, or you hope it gets. What the model is essentially is a pattern recognition machine. It gets 101 past data and it can plot it out into like a pattern, right? And what it does is it recognizes that pattern and attempts to guess the next sequence of it, which is tomorrow's price. It's a pattern recognition machine, and it guesses the next step in that pattern. That's like what the model does. Yeah. And the reason why I think, I'm going to get to like my thought process a bit here. The reason why I think that the model is more suited for large market cap companies is, well, if you just think about it, the biggest 50 companies in market cap, the Mag 7 is in it, right? Okay, yeah, the biggest 50 companies, there's a Mag 7 inside of it, right? It has to make sense that way. Those companies are very correlated with the S&P itself. If the companies go like up 1%, chances are the stock market, the S&P that day goes up 1%. They're very correlated and they are very similar. Essentially, that means when we train our model on these different stocks, let's say Google, Amazon, and Apple, right? Those three. We're just repeating the data. The patterns, they look so similar that the model is trained on the same data 3 times. Effectively, not literally, because the price is always different, but effectively that's what it is. That's a form of overfitting almost. You're training the model on the same data or similar data with like very little nuance to it. Which is why in my case here, I'm kind of looking for overfitting. I hope that makes sense. Okay, so back to the actual function. It just loops through the entire dictionary, takes the X train and the Y train from the dictionary that we compiled in the previous function. And then since we have the X train and Y train, we can actually, train the model. We save it into a folder, which is right over here. Models, nope, not this one. In model. So we have model, the subfolder is market cap because that's the one that I tested. And then these are all the models. They're on the GitHub, they're on the repo. So you don't have to worry about training it because this probably took me 5 hours to train this. And then the other model, the base case model, it probably took me another 5 hours to train, which is a little inconvenient, not gonna lie. So it trains the model. This essentially just initializes it with certain parameters. And then for every single box, every single, the 10%, the 0 to 10% market cap, the 10% to 20% market cap, the 20% to 30% market cap, and so on and so forth, it trains one model on each of those. So you end up with 10 different models. Okay, so that's training model. Testing model is the same thing. It loops through the entire dictionary that we got from the previous function, and it gets the X test and the Y test in this case. It loads the model from the folder so you don't have to train anything else. And then it predicts. It predicts using like obviously the model input with X test to get the Y prediction, what the model thinks Y should be. You compare it with Y test by using, there's different ways to do it. There's mean squared error, there's mean absolute error. I used mean absolute error in this case because it just made sense to me, like intuitively. I don't know if I'm right or wrong in this. So yeah, then it just prints, oh, this absolute error is whatever number. I also calculated the average error without that. It's not the most accurate thing. The absolute average error is probably the more accurate error assessment. This just lets me know if the model regularly under predicts or over predicts the whatever price. If it's a negative number like negative 0.2, then I know that on average the model under predicts by 0.2. Though not accurate, like it's not, I know for certain that the model always predicts like minus 0.2%. It's just, it's a general like idea that I get. Okay. So that's like all the functions, and what it ends up with after training all that, after doing all that is this. Let me just show you. I already ran the functions, so you don't have to see it. Let me open this up. Okay. So after compiling all the data, this is training for the 10% box. These are the 10% lowest market caps in the S&P 500. And the average absolute error is almost 1%. I already converted it. The one here is not 100%, it's 1%. So on any given day, the model for 10% box is wrong by 1%, roughly. And it routinely underguesses by this much. Not with 100% certainty, but it routinely does. If that makes sense. So that's 1% roughly. And then we move on to 20%. These are the lowest 20% market cap, or in between 10% and 20%. So they have more market cap than the 10% box. And you can see the error is going down slightly, right? We move on to 30%, the error is going down. 40% error climbed up again, but it's a trend. We're looking for a trend, not like the actual values. 50%, see it's going all the way down again. 60%, it's a bit up, but it's still going lower. 70%, we have 0.87%, which is dropping drastically. The 80% box, we have 0.89, which is, it's okay. 90%, which is 0.87, and then 100%, which are the top 10% boxes, they have an average error of 0.84%. That's not good, by the way. Like, I just want to be clear. That is not good. It is not good because like the average movement of a stock in the S&P 500 is like 1% a day. And you're wrong by literally that amount. Like, for example, if Google went up 1% today, your model would have a 0.84 difference from that. Essentially meaning you guessed that it was like Google would only go up by 0.2 or Google would go up by 1.8%. That is a lot of money that you will lose from this model. Like, it is not a model that you should actually use for a like a money making trading strategy, whatever. It's just for me to test my intuition on, hey, I'm trying to apply like fama-french intuition to another aspect. I'm just testing it out. I'm trying to learn machine learning shenanigans, right? And it kind of proved itself. Okay, we're back. I just wanted to touch upon some miscellaneous stuff that I did. Some things that didn't make it into the main part of the project. So over here, I did a few functions, and the goal of it was to access financial statements from the SEC filings. I wanted to do that because they had historical data and I wanted to compare it using that. However, the problem I ran into was that it was just too difficult and too it was just too difficult to parse. I just didn't really understand which dates I should have been looking at, which I should have dropped, which I should have kept. And overall, I left it in here, but I'm not going to explain too much of it. I did a few other stuff here. This is a testing the baseline of an index function. Please don't mind my variable names. I kind of started losing my mind by the end of this. But essentially what this does is that it takes the full list of every single ticker in an index in a CSV file, and it trains a model on all of it together. So previously with the functions that I showed above, it splits it up into a group, into groups of 10, into 10 groups, sorry. So there's 10 groups and a model is trained on each of the groups. So there are 10 models and then they're tested on those 10 models, right? But what if it was all just one group with no sorting whatsoever? This is testing the baseline. And essentially what we're trying to do is just compare the number that they get here, the baseline function gets, to the actual, I guess like the thing that I'm testing, the theory that I'm testing. The number we get, the absolute error, is this 0.96, and comparing it to the 90% to 100% box, it is higher. This box is lower, which kind of confirms the logic behind what I was testing for. Basically, large caps are easier for models to predict than their small cap counterparts, and overall splitting it into groups for the machine learning model is a lot more effective than just clumping them all together and putting it into one model. Sometimes more data isn't actually the solution. It is more curated data. So that's what we ended up with. As for next steps, what I want to try out, there's a particular list that I created, metrics that I want to test. This is a list of a bunch of metrics that are available on Yahoo Finance, and I really wanted to test some of them. I landed on market cap because it just intuitively made the most sense, as I explained previously. But a lot of these metrics in the metrics I want to test, and combinations of these metrics, could yield even more effective models or show even stronger proof that certain models or certain data sets, certain subsets of these metrics lead to more accurate models. And that's what I'd like to test. That's one of the things. That's probably the biggest thing. That's why I say the project is more like 90% complete. Another next step I'd like to do requires us to look at the very first function I made. Okay. Here, we scaled the data from everything, every single stock price data. We scaled it to a value between 0 and 1. That doesn't change. The value stays between 0 and 1 throughout the entire process. So if you asked me for a specific price at a specific date for a specific stock, I couldn't actually give it to you. I couldn't actually predict it for you. I can only show you the accuracy, not necessarily the price itself. In order to do that, I'd have to set this and essentially chain it along every single other function, having this return x train, x test, y train, and y test, and then along with that, the scaling factor here, and then bring that all the way along for every other function, and then unscale it someplace else. But those are the general two things that I'd like to work on top of what I've already done. Okay, so yeah, that's basically my project for now. If you have any questions, just like message me or something. I'm looking for feedback if you guys think this could like use any improvements, if I'm doing anything like blatantly wrong or misguided. Yeah, because I personally don't think this project was too crazy. I think it took me maybe 2-ish weeks to work on the seventh one at least. Total, it took me the whole summer, I think. But I don't think this project is too complex yet. If I keep on adding things, like if I start finding combinations of these metrics, if I start doing it in real time, because right now we're only taking the most current of these metrics. If these metrics could be taken in according to time, maybe even the S&P 500 index could be changing. As in the S&P 500 index we have right now, that's the current one. What about 20 years ago when the S&P was different, right? That could change up the data in so many different ways. So yeah, I don't think I've done the most that I can do. So I'm looking for feedback on how to improve this. And yeah, hope you guys kind of learned something. Hope you guys, yeah, enjoyed this.